Hi, hello everyone. This is the educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. So do watch this session. If you like it, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright? And you can also visit our website www.v-learning.in. You will be getting all these lectures there. Along with that, you'll be getting lecture notes in PDF format. You can download them, you can learn from them. Okay? Now, without any delay, let's get started with today's session. We were doing moving charges and magnetism, and this is lecture number 7. In this lecture, we are going to see Ampere Circuital Law. So it is a new law. Last session, we studied about Biot-Savart's law. Right? Here we'll be talking about this particular law, and then we'll be seeing magnetic field due to an infinitely long straight current carrying wire. Now this is something which we have already seen in last session, right? Infinitely long straight current carrying wire, and that we have found out using Biot-Savart's law. Here we'll be finding out magnetic field due to this using Ampere Circuital Law. All right. Then magnetic field due to a current carrying cylinder. Current carrying cylinder basically means a thick wire, you can say. If a wire is very thick, it is like a cylinder, right? So it's the same thing. Alright, in this we'll be talking about two different cases, where in the first case the current will be at the surface of the cylinder. Inside there will be no current. Second, the current will be distributed throughout the cross section of that cylinder. Alright, in that distributed throughout the cross section also there will be different cases. One case will be distributed uniformly. Alright, second will be distributed non-uniformly. In non-uniform distribution, again many ways are possible for distributing it non-uniformly, right? We will be discussing one case of non-uniformly distributed, so that you will know how to do this kind of problem, and rest you can do on your own. Alright, let's start. Ampere Circuital Law. See, this law is used to anyways take out magnetic field only. Fine. In first chapter, if you remember, we studied about Gauss Law. First we studied about Coulomb's law, then we studied about Gauss Law. From Gauss Law, we used to take out electric field due to continuous distribution of charges, right? If the distribution is uniform and symmetric, then we used to make a Gaussian surface around it, and we used to find it, right? Ampere Circuital Law is also somewhat similar. Okay, you can say it's like a cousin brother of Gauss Law. There we used to assume a Gaussian surface. Here we'll be assuming an Ampere's loop. There we used to use Gauss Law to take out electric field. Here we will be using it to take out magnetic field. Okay. Now suppose there are more than one wires. If one wire is there, we know the formula. Correct? More than one wires are there, using the formula, adding them again and again. If 10 wires are there, then add it 10 times and you will get the magnetic field. But here by this law, it becomes easy for more number of wires if they are present in an area. Clear? Let's say there are two different wires. In one wire, current flowing is I1, which is upwards. In I2, current flowing is downwards. Now at point P, I want to find magnetic field. Alright, so what I'll do, I'll assume an Ampere's loop here. It's a circular loop. If I show you the top view of this, it will be something like this, where I1 is coming outwards. From top, we are seeing this, okay, it's the top view. I1 is coming outwards, I2 is going inside. At point P, I have to find magnetic field. So what I'll do, I'll construct an Ampere's loop. This is Ampere's loop. Okay. Clear? In Gauss Law, if you remember, we used to assume surfaces. Here it's a circular loop. Clear? It's length. It is length basically. There we used to take out the area. Here length it is. Okay, if I cut it from here, it is like a rope, it is like a thread basically. Alright, there it was a sphere, here it's a circular thread, it's a circle basically. Alright, if you remember in Gauss Law, the formula was something like closed integral E dot dA is equal to charge inside upon epsilon naught. Are yes or no? I'm just writing to make you compare the things, okay? Because comparison makes learning easy. See here, E dot dA is equal to charge inside the Gaussian surface upon epsilon naught, which was the constant. Here, Ampere Circuital Law, what it says, integral, there electric field was there, here magnetic field will be there, B. Their area was there, here length will be there, dot dl, no doubt these are vectors, that is equal to, there the coefficient was, the constant was epsilon naught, here it will be mu naught, right? There it was charge, here it will be current, and there was charge inside, here it will be current inside. Alright, this is Ampere's Circuital Law, note it down. This is Ampere Circuital Law. Line integral, this is line integral. Line integral. Clear? This dl. Integral b vector dot dl vector is equal to mu naught into I inside the loop. Now if I ask you in this particular case, how much current is there inside the loop? Some people will think, oh, I1 is also inside, I2 is also inside, current will be I1 plus I2. No. Direction also matters a lot. Okay. Net current, we have to write how much net current is there inside. Okay. Here if you see, this I1 is coming outwards, I2 is going inside. Completely opposite direction, right? So it will be I1 minus I2. Current inside will be, you can also write I2 minus I1. I inside can either be I1 minus I2 or it can be I2 minus I1. Then how to choose which one is correct? So what we have to do is, what we'll do first, while constructing this loop, we'll be considering a direction also for the loop. Okay. Direction can be any direction. You can consider a clockwise direction. You can consider an anti-clockwise direction. It is completely according to your convenience. Okay. Here, let's say I have considered an anti-clockwise direction. Fine. Whichever direction you consider, curl your fingers in that particular direction, then the direction of thumb will be taken as positive. Alright? Whichever direction you have taken, curl your fingers in that direction, then the direction of thumb will be taken as positive. So whichever current is in the direction of thumb will be taken as positive current and the other one will be taken as negative current. So here if you see, the thumb direction will be outwards. So this current is coming out. So this will take positive, this will take negative. So I inside will be I1 minus I2. Clear? Got the point? Alright. So now, note it down. If you want to note down all the steps, note down. Suppose we have to find the magnetic field due to current carrying wires. First step, construct a loop around it. Whatever I have explained, it is just in words. Choose a direction of loop, clockwise or anti-clockwise. Okay. Then curl the fingers in the direction of the loop and take the direction of thumb as positive. Current in the direction of thumb will be taken as positive and opposite to the direction of thumb will be taken as negative. Then apply Ampere Circuital Law, which says integral b dot dl, b vector dot dl vector is equal to mu naught into I inside. Clear? Now here, what is this dl basically? B we know is the magnetic field at this point. What is this dl? How do we integrate this dl? This dl is not the distance of this from this. We used to take that dl in Biot-Savart's law. Actually in Biot-Savart's law, what we used to do, we used to take dl in the wire. If this is the wire, then we'll take small dl and then we'll take this. No. Here this dl is not this length. This dl is not the part of the wire. This dl is part of this loop. This is dl. Clear? If I have to find at this point, we'll take this as dl. Clear? So here this direction of the loop will be the direction of dl. For this small part, if I am taking it as dl, it will be a straight part only because it is very small, correct? So this direction will be same as the direction of the loop will be the direction of dl. All right. So this small dls will be integrating this small dl. If I integrate this dl fully, dl, I'll get the circumference of this loop, correct? That's what dl is. Got the point? Now, I hope you have noted it down. If you want, you can take a screenshot of it. I'll go out of the screen and count till 3. 1, 2, 3. All right. Next. Now see, this Ampere Circuital Law is valid everywhere, but is useful only in few cases. The same I told you in Gauss Law also, if you remember, that it is valid everywhere, but it is useful only in few cases. Because then otherwise it will become very difficult. It is useful only in symmetric cases, right? Here also, this is also valid everywhere, but useful only in highly symmetric cases. Okay, let me just write down the cases for you where this particular law is useful. Okay, this law is useful if first, see, the formula is this. I have to make this formula useful. When this formula can be useful for us, when the calculation becomes easy, as simple as that. If the calculation is tough, then there is no point of using it. So what we'll do, see, when this will become easy, if B and DL, the direction of B and DL is same. Why? Because if the direction of B and DL will be same, this vector sign, if I remove, it will come as B DL cos theta. If the direction of B and DL is same, then cos theta will become cos 0. Then it will simply be B DL, that's all, right? Cos 0 is 1, so it will be integral B DL. And if B is constant, then I can take out this B outside of this integration sign. It will be B integration of DL. So B integration of DL is easy, right? So this law is useful if B is tangential, B vector is tangential to DL vector. Tangential means the direction of B vector and DL vector is same. And B is non-zero and constant. B is non-zero and it is a constant. So what will happen with this? Integral B dl cos 0 will come. That is equal to mu naught into I inside, correct? From here, if B is constant, we will get B integration dl is equal to mu naught into I inside. So now see, this integration is very easy for us. Let's say this is the circular loop which I was talking about. This is a circular loop. Now B is constant. It will come out. Integral dl will be 2 pi r. Whatever will be the radius of the circle, 2 pi into that radius will be integral dl. It became very simple, right? Tangential means, again I am telling you, B vector and DL vector are same. Here in this case, why I have made this Ampere's loop? Because we can, this Ampere Circuital Law is useful for this case. How? See, if I take the direction of this loop as anti-clockwise, the direction of DL here at this P point will be upward. So I told the current which is coming out will be taken as positive. So I1 minus I2, if I take, the net current will be outward. So net current is outward. Current into this distance, this vector, right? If you remember Biot-Savart's law, I cross DL to get the direction of magnetic field. Okay, how do we get the direction of magnetic field? This fingers in the direction of current, curl it in the direction where we have to take out the magnetic field. Then the direction of thumb will give the direction of magnetic field. See, magnetic field is also coming upwards, B vector. So now since DL vector, B vector are same, this is called tangential. See, both are tangential. Here also if you take out, B vector will come like this, DL vector is in this direction. Both are tangential. So in this case it is useful. B is a constant, it is non-zero and it is tangential. All right. Second, if B vector is perpendicular to DL vector, then also it is useful by integral B vector dot DL vector will become 0. Are yes or no? See, B dl cos 90. If B vector is perpendicular to DL, B dl cos 90, cos 90 is 0. So this will become 0. If this becomes 0, again the calculation is easy, right? Third, if B becomes 0. Why? Because if B becomes 0, then again this integral B dot DL will be 0. Calculation will become easy. So in these three different cases, you can use Ampere Circuital Law. All right. In NCERT, what is written is Ampere Circuital Law is only valid if these three conditions are there. That is not true. Ampere Circuital Law is valid everywhere, but is useful only when these three conditions are there. All right. But let's say in your board exam, if it comes that write 3 points where Ampere Circuital Law is valid, then you have to write this only because this is given in your NCERT. All right. Now, next, let's say there are 4 different wires. Okay. I have to find magnetic field at point P. What I can do? If you see this point P, if the point was here somewhere, let's say, I could have made a bigger circle like this, correct? Of let's say some radius r. B dot dl, integral B dot dl is equal to mu naught into I inside. I inside would have been, if I take this as anti-clockwise, this current I can take positive, I1 minus I2 minus I3 minus I4, I could have taken out, right? But here this time, the point is, point P is here. And the loop which we have to construct should be in such a way where it should go across this point, go through this point P. So if I make a loop going through this point P, it will come something like this, right? So now, see, I have made a loop. This is Ampere's loop. I'll consider any direction. Let's say I consider this direction. The Ampere Circuital Law, what I will use here is B integral dot dl vector. Integral B dot dl is equal to mu naught into I inside. How much will be I inside? If I consider this as anti-clockwise, I1 minus I2. Or first I'll write I inside. Using this, the magnetic field B, what you will get will be due to all the 4 wires at this point. Clear? Although the loop you have made around these 2 wires, but the magnetic field will be due to all the 4 wires. If you remember in Gauss Law also, let's say there were some charges are there, charge 1, charge 2, charge 3, charge 4, charge 5. If I make a Gaussian surface like this, the magnetic field will be due to all the charges. But whenever we have to write Q inside upon epsilon naught, in that Q inside we used to write only the charges which are inside. Correct? That is the beauty of these laws. So now here if you see, this inside will be only these 2 currents, but this magnetic field is due to all. Always remember this B due to all the currents. This I inside is only the current which is inside. Clear? Note it down, very important. Magnetic field, this magnetic field here, whatever we'll get will be due to all the wires. But this current which we are taking, that is the beauty of this particular law, that by using this we can get the magnetic field due to all the wires. Okay? Done. Next. Now this Ampere Circuital Law is over. I hope you understood it. Let's apply it. Let's see the applications. Magnetic field due to an infinite current carrying wire. So there is a current carrying wire. infinitely long at point P, which is at distance r. I have to find magnetic field. We have already done this through Wyatt-Savart's law, if you remember. What was the magnetic field? Mu naught I upon 2 pi r, correct? Due to finite wire, mu naught I upon 4 pi r into sine theta 1 plus sine theta 2. Theta 1, theta 2, if becomes 90 degrees, then sine theta 1 plus sine theta 2 becomes 2, right? And that 2 and the denominator 4 used to cancel. So mu naught I upon 2 pi r. So this should come using Ampere Circuital Law also, because that is the magnetic field due to infinite wire. Let's see using Ampere Circuital Law. So what we'll do, we'll make an Ampere's loop around it. Let's see the top view. This is the top view. The current is coming out. At this point I have to find, which is at a distance r from this wire. Let's consider a direction. I'll consider a direction anti-clockwise. If I consider a direction anti-clockwise, this dl, the direction will be upward. This magnetic field due to this wire, see, it will also be upwards at this point. B will also be in this direction. Correct? Ampere's law, if I will write, integral B vector dot dl vector is equal to mu naught into I inside. Correct? Now B and dl are having same direction. So cos theta will be cos 0 will be 1. So I can write this as B dl cos 0 is equal to mu naught into I, because I inside is nothing but I. Correct? Cos 0, this will be integral. Now this B is constant. B will come out. Integral dl is equal to mu naught into I. Integral dl is dl, if I integrate for this entire circle, it is the circumference. That is 2 pi r. So B into 2 pi r is equal to mu naught I. From here, B is equal to mu naught I upon 2 pi r. See, the same formula has come. B is equal to mu naught I upon 2 pi r from Ampere Circuital Law. Got it? How to do? Note it down. Now, some people will think, sir, every time you are considering anti-clockwise direction only. See, anti-clockwise direction why I have considered, because the current is outward. So if I consider anti-clockwise, my thumb is outward, which is the positive thing, right? I told that curl the fingers in the direction of the loop, then the thumb will give you positive direction. If the current is in the direction of thumb, this current I will take positive. That's why I have written here I. Now let's say I consider a clockwise current. Okay. Here if I consider clockwise, then what will happen? This dl direction will change. Okay. Let's say dl direction will change. So now this will become B dl cos 180. Right? Integral B dl cos 180. Because the directions are opposite, and that is equal to mu naught into I inside. How much will be I inside this time? Minus I. Why? I told curl the fingers in the direction of loop, then your thumb's direction will be taken as positive. This time thumb's direction is inside. That means inside I have to take positive. Whichever current goes inside should be positive. But here this current is coming outside. So this current has to be taken as negative. So this is minus I. Now from here, B dl cos 180 means a minus sign will come here is equal to mu naught into minus I. See, this minus will be cancelled. Again the same thing only. Minus since it's become cancel, now dl will be 2 pi r, this dl will come down mu naught I upon 2 pi r. Answer will be same. Alright, you can take any direction, whether clockwise or anti-clockwise. Answer will be same. Alright, because the direction of current will also change. Sorry, the sign of current will also change. Clear? I'll do it like before. Next, magnetic field due to a current carrying cylinder. Now current is on the first case will be current is on the surface. So there is a thick wire or a cylinder, current is on the outer surface of that cylinder. Okay, let's see. First case will be R less than R. Forget about this for now, just see how it is. So this is a cylindrical wire, current is on the surface. I have shown you by sides so that you can understand it is on the outer surface. Okay, total current is I. The radius of this cylinder is R. Now here it is written R is less than R, means we are talking about the magnetic field inside the cylinder. Inside the cylinder. Alright. Let's say there is a point P which is at a distance R. This R is smaller than R, that means we are talking about inside the cylinder. We have to find out magnetic field here. For those who are not able to understand, I will show the top view of this, how it will be. So this is a cylindrical wire, this is the top view, from top I am seeing. The current is on the surface like this, outer surface. Current is coming outwards, right? From top if you see, current is coming upwards. So this is coming outwards, right? There is some point P here, which is at a distance of R. Here I have to find the magnetic field. So what I will do, I will make an Ampere's loop here, correct? Now after making the Ampere's loop, I can write down integral B dot dl is equal to mu naught into I inside, correct? Now let's say the direction of loop and the direction of dl, everything I have taken in such a way that cos theta is cos 0 degrees, okay? So now this will become integral B dl is equal to mu naught into I inside is, mu naught into I inside is, I inside, how much is I inside? 0. This will be 0 since I in is 0, correct? Inside this there is no current, whatever current is there is outside. So that will be 0. So this integral dl, B is a constant, integral dl is 2 pi r. B into 2 pi r is equal to 0. 2 pi r is not 0, right? That means what is 0? B is 0. So from here, B is equal to 0. 2 pi is a constant, r is the distance, which is again not 0. That means B is 0. So B inside this is 0. Clear? In a cylinder, if the current is at the surface, inside the cylinder at any point, magnetic field is 0. Done? Easy to understand? Alright. Next. R is greater than R. R greater than R means we are talking about any point which is outside the cylinder. Outside the cylinder. Clear? Let's say there is a point P which is at a distance R which is outside the cylinder. Top view if you see it will be like this. The current is at the outer surface. Radius R. The point P is outside the cylinder. First I will take an Ampere's loop. Alright. Now let's take the direction of Ampere's loop as anti-clockwise. Again you can take any direction. Why I am taking anti-clockwise? Current is outwards. Fine. Current is outward means current is like this. At this point, if I have to take the magnetic field will also be this side. So dl's direction is upward and magnetic field will also be upwards. As simple as that. Fine. So direction anywhere. If I see at this point dl, if I take this, magnetic field will be this. At this point dl, if I take this, magnetic field will also be in this direction. Magnetic field is tangential. That's why we are able to use Ampere's law. Correct? We discussed about 3 conditions, right? Here magnetic field is always tangential to dl. That's why we are able to apply Ampere Circuital Law. So integral B dot dl is equal to mu naught into I inside. This will be integral B dl cos 0. That is equal to mu naught into I inside. How much I is there inside? Complete current. I told the entire current is I only, right? So this is I. All the current is inside. So B integral dl is equal to mu naught I Cos 0 is 1. Integral dl means dl. If I integrate for this entire circle, I will get 2 pi r. So b into 2 pi r is equal to mu naught I. So b is equal to mu naught I upon 2 pi r. Clear? Is the same formula which we got for the infinitely long current carrying wire, right? So now from this formula, if someone tries to understand, it is like, it seems that the current is at the center. The current is flowing, there is a wire in which the current is flowing, current flowing is I, and we have found out magnetic field at a distance r from this wire, correct? From this formula, this is what we can understand, right? Current is not at the center, current is only at the surface, but it seems, from this formula, it seems like current is at the center, and from the center at a distance r, we have taken out magnetic field. Clear? In Gauss law also, if you remember, in the case where at the surface the charge was there, but if you are finding outside the cylinder or outside the sphere, it was like the charge is concentrated at the center, right? Similar. Now, I hope you understood both the cases of when the current is at the surface. Now we'll be talking about when current is distributed. Acha, before that, plot for B versus R. For this case, when the current is at the surface. So inside this cylinder, we have already seen that till here. Let's say this is B, this is R. So when R is equal to the radius, till here, the magnetic field inside is 0, correct? And suddenly the moment this small r crosses R, when it comes outside the cylinder, if you have to see, magnetic field increases. Suddenly it becomes, it gets some value, right? And then it starts decreasing. See here, B is inversely proportional to R. Correct? So this will be, B is inversely proportional to R. B is equal to mu naught I upon 2 pi R. Outside the cylinder. B is equal to 0 inside the cylinder. Right? On the surface, this R, make it as capital R, mu naught I upon 2 pi capital R. Clear? Next, current is distributed uniformly in the cross section. So now, first case is small, the point is inside the cylinder, okay? So this is the cylinder. Now this time the current is distributed inside, complete. The wires, if you see from here, it will be like this. I'll make the top view, you'll understand. Alright. There is a point P inside, which is at a distance r from the center. The radius of the cylinder is capital R as usual. Top view, if I make, this is the cylinder. The current this time is like this. Full inside in this entire cross section, the current is coming outwards from that. Fine. The point P is inside it at a distance r. So first step, what we'll do? We'll make an Ampere's loop. We made an Ampere's loop, right? For this, if I want to write the Ampere Circuital Law, I can write integral B vector dot dl vector is equal to mu naught into I inside. The same thing. But now see here. See here. I inside. In the previous case, I inside was 0. There is I. How much I is there inside? How much I is there inside? If in this entire cross section, which is 2 pi r, by unitary method we can easily find out. For 2 pi, for cross section, in pi r square, the current is I, correct? In entire pi r square, capital R square, right? In this entire cross section, in this entire pi r square, the current is I. So in this much, how much current will be there? In 1 unit, the current will be I upon pi r square. 1 unit area. So in pi small r square, how much current will be? I upon pi r square into pi small r square, correct? This will be the current which will be there inside this. So one way is through unitary method. Another way, you can assume the surface charge density. Since it is uniformly distributed, J will be equal to I by A. Correct? Now, for what does this mean? This means that in this entire area A, current distributed is I. So that means this will be equal to, since it is uniformly distributed, it will be constant for this entire thing, right? For this area, current inside will be equal to area of the loop. Correct? So I can write J is equal to I by A, and that is also equal to current inside upon area of loop. The ratio has to be same. For this entire thing, if I take I by A, the same ratio should be there for the current which is there inside divided by this area, because it is uniformly distributed. Right? So this is current density what we have taken out. Solve this. I inside is equal to I upon A into area of loop. That's what it is written. I upon the A. This A is the area of this entire, right? I upon A into the area of the loop. I upon A into area of the loop will give you I inside. The same thing. Either you can do by unitary method or you can do by that. Clear? Now we can write it. This will be integral. Now see, B and DL. B will be at this point, if you see B is upwards, I will take it anti-clockwise, so DL will also be upwards. Alright. Net current is outward, anti-clockwise, thumb is this direction, current will be positive, I have to take current as positive. All those things are very simple. So this will be B constant, B will come out, B integration DL is equal to mu naught into I upon pi r square into pi small r square. Correct? Cos theta is cos 0. Both are tangential at any point if you see. DL, integral DL will be circumference of this loop, Ampere's loop, 2 pi small r. Mu naught, this pi and pi will be cancelled. From here, I r square upon capital R square, 1 r and 1 r will be cancelled. B is equal to mu naught I r divided by 2 pi r square. B is equal to mu naught I r divided by 2 pi r square. Note it down. Easy? Now from here if you see, B is directly proportional to R. See, this R is constant, it's the radius, it is directly proportional to R. So inside the cylinder, from center to this, till the time it comes outside, to this, it is directly proportional. Outside if we have to see, it's again the same story. This entire current is there like this. If you see the top view, it will be like this. The point P is outside. Outside means we'll take an Ampere's loop. From this Ampere's loop, let's take the direction anti-clockwise. Here if I take DL, that DL will be upwards. This is DL, right? B vector will also be upwards at any point if you see. At any point if you see, B vector and DL vector will be same. Integration of B dot DL is equal to mu naught into I inside, right? From here, B integral DL, cos theta is cos 0 is 1, that is equal to mu naught into current. How much current is there inside? Total current is there inside. How much is the total current? I. that is I. So B into 2 pi r is equal to mu naught into I. So B is equal to mu naught I upon 2 pi r. The same story, the same formula, as if the current is concentrated at the center. The same. Okay. Outside the cylinder, whether you take the previous case where the current is only at the surface or here where the current is distributed, it will be same, mu naught I upon 2 pi r, because now we are seeing at a point which is outside. From outside, if you see, we have covered the entire current, how much ever it was there, right? So again, it seems that the current is only at the center. Done? Easy? Now here again, if you see, B is inversely proportional to R. So now if I see the plot, till here, if I take this as small r, this as B, till here, B is directly proportional, correct? B is directly proportional to R. From here again, it starts decreasing like this. B is inversely proportional to R. This will be the plot. Clear? Shall we go further? All right. Now we'll see the third case. Current is not distributed uniformly. Again, there are many ways to distribute current. Many ways. We'll be seeing one such way, where in this case, if the current density is J is equal to J naught R, where J naught is a constant and R is the distance from the center. Okay. So this time, current density will actually tell whether it is uniformly distributed or not. If it was a constant, that means uniformly distributed. Since it is not a constant, it is dependent on R, where R is the distance from the center. So how much far you go, current increases from the center, right? So that's what this tells. J is equal to J naught R. So here this time, this is a cylinder. Current is there throughout inside, but it is not uniformly distributed. Inside the cylinder, at point P, which is at a distance small r from here, we have to tell the magnetic field. Top view again will be, this time I have removed the outer circles. So this dot dot means the current is coming outwards, okay? At point P, at distance r, I have to take magnetic field. What I will do? First thing, Ampere's loop. Try this on your own also. Very important it is. Okay, these kind of questions will actually make your concept more strong. All right. Now see, here again the formula will be same. Ampere's law is Ampere's law, that is B vector dot dl vector is equal to mu naught into I inside, same. The only challenge here is to find I inside. Once you get I inside, everything is same. dl, see, B is a constant, correct? dl will be integration of this entire thing, dl will be 2 pi small r. Integration of dl is 2 pi small r. Mu naught is a constant, I inside only you have to get, correct? Now see, again since the current is outward, I will take this as anti-clockwise. So here if I take a dl, which will be upwards. Magnetic field also, since current is outward, at this, if I take magnetic field will also be upwards, right? Cos theta is 0. So this will be integration, B will be outside, dl, that is equal to mu naught into I inside. So that is B 2 pi, how much is this? 2 pi r, mu naught into I inside. So B is equal to mu naught I inside upon 2 pi r. The main thing is to get I inside. Let's get I inside. How do we get this I inside? See here, this current density is J is equal to J naught R. That means it is not uniformly distributed. As we are moving outside of this point, moving away from this point, the current is increasing, right? Let's take a random distance x. From here, at any distance x, I am going to consider a ring, okay, of thickness dx. Thickness is dx, fine. Now in this ring, there will be some current. If I want to write the current in this ring, can I write? J is equal to, current in this ring will be di, some small di. Current will be small di, and the area of this ring will be dA. Current density will be equal to di by dA. Are yes or no? J is equal to I by A. That we know, right? Now, since here current is not uniformly distributed, but for this small area I can consider it as uniformly distributed. I know for this entire area it's not uniformly distributed, but since this area is very small, it's a very thin ring, for that thin ring I can consider that current as constant, right? So for that I can write J is equal to di by dA. That means di, if I want to write, that will be J into dA. Correct? From here, J is J naught into R. R is the distance from the center. Here, distance from the center is X. So J naught into X into dA. Are yes or no? For small current, I have considered current is constant in this cross section dA. From there, I got di is equal to J into dA. From here, di is equal to J naught X dA. Right? From here, now what is dA? dA is the area of the small ring. What is the area of this ring if the thickness is dx? If I cut it, it will be a straight rectangle like this, right? It's a ring. The thickness is dx and the length will be 2 pi x, the circumference of this. Correct? Area is 2 pi x dx. So this will be di is equal to J naught x 2 pi x dx. Integrated, we will get the current which is inside. If I integrate it, the current inside will be, see, this will be I is equal to, I inside is equal to, J naught is a constant, 2 pi is a constant, x into x, x square dx, x square dx is, integration of x square dx is x cube by 3, x cube by 3, and we are integrating from 0 to r. Are yes or no? Because Ampere's loop, I inside means what? Whatever is there inside this loop. This inside is at a distance r. From 0 to r I am integrating. So from 0 to r if I integrate, this will be J naught 2 pi r cube by 3, that is I inside. Correct? Substitute this I inside. Substitute this I inside here. B is equal to mu naught I in upon 2 pi r. B is equal to mu naught I in upon 2 pi r. That is equal to mu naught into 2 pi r cube by 3 by 3, and this 2 pi r is also there. Now see, 2 pi cancelled, 1 r, and from 1 r here will be cancelled. Finally we will get B is equal to mu naught. Okay, one more, J naught is also there, right? J naught into 2 pi r. J naught 2 pi r cube by 3. From here if you see, this 2 pi will be cancelled, 1 r will be cancelled. What we are left with? Mu naught J naught r square by 3. For this particular case, where current density was J naught r, our magnetic field is mu naught J naught r square by 3. I hope you understood how to proceed with this kind of question, right? It was very simple. Everything was completely same. Integral B vector dot dl vector is equal to mu naught into I inside. Begin with this, right? Solve everything. The main thing is to get I in, because the current was not distributed uniformly. We did integration to find the current. All right. Done. Easy. Today's lecture was really easy. It was interesting also. Just try to revise it once again. Okay. Try to get the answers of all kinds once again. The first one, infinite wire, right? Try to understand Ampere Circuital Law. Then get the value of magnetic field, the formula, the expression for magnetic field due to infinitely straight current carrying wire, then due to a cylinder where the current is at the surface, inside the cylinder, outside the cylinder, then due to a cylinder where the current is distributed uniformly throughout the cylinder, throughout the cross section of the cylinder, inside and outside both, and then where it is non-uniformly distributed. Practice this also once. All right. In the next session, we'll be doing magnetic field due to solenoid and magnetic field due to toroid. Again, very interesting session. I hope you liked today's session, you understood today's session. If you like today's session, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. All right. You can also visit our website www.v-learning.in. You will be getting all these live sessions there. Along with that, you will be getting lecture notes also in PDF format, which you can download and learn from them. They are very useful. Again, do check it out. We'll meet up in the next session. Till then, keep learning from V Learning. All the best.